All right, greetings everyone. Welcome to the video for section 3.1. And I'm very excited for this because this, y'all, is where we really get into the reason you came to calculus. So this section really starts to get at the heart of what calculus is about, or at least calculus 1. So I'm really excited to be jumping into this stuff. Okay, so if you recall back when we started our new material, we started talking about tangents, tangent lines, and secant lines and the relationship between the two. And if you recall, we were able to find slopes and equations of secant lines fairly easily, but we saw that there was a problem when we started to try to find the slopes of tangent lines. And so here, today, we're going to remedy this. So what I'm going to do, first of all, in this picture is add some coordinate axes, so some input and output axes. Okay, and notice what we've done, or actually what we have here. We have a function f of x, so that's the curve there that kind of looks like a parabola. And we've identified an input value a right here, and then we have that point up there that is a f of a, so what we get when we input a into the function. And then we've identified a second input value over here that we're calling a plus h. So the idea there is we had a and we added a little bit more to it, so that's what that value h gives us or represents. And so that gave us the point a plus h, and then up there we have the inputs and outputs related to that point. Okay, and you'll notice that when we connect those two dots, we've got a secant line there. How do we know it's a secant line? Well, because it touches the graph in two different places, right? And if we recall, we talked about finding the slope of that secant line. So m sub secant is what I'm going to call that. And if you recall, when we find the slope of a line, that's where we use our y2 minus our y1 over our x2 minus our x1. We can label these points that way. So I'm going to call this y2, this y1, this will be x2, x1. So when we calculate the slope now, we'll have f of a plus h minus f of a all over, we do the differences in the inputs, so we'll have a plus h minus a. And then notice we can simplify this a little bit because we have a plus a and a minus a in the denominator. Those will cancel. So we end up with f of a plus h minus f of a all over h as the slope of our tangent line, or our secant line, excuse me. Okay. All right. Now let's talk about finding the slope of the tangent line. And if you recall, when we were talking about the relationships between tangents and secants, we saw that if we take this second point here, this a plus h and f of a plus h, and start to move it back along the curve, which in this case would represent reducing the value for h, right? So hopefully you agree with me that if we take the value of h here and we start to move it down or reduce it, that's going to move the point a plus h closer and closer to a. And if we move it all the way back, so we make the value of h actually equal to 0, we'll notice that what happens then is a plus h just becomes a, and the point up here at a plus h comma f of a plus h will just become a f of a, right? And so in that case, if we're going to find the slope of the tangent line, well, m sub tangent then would be f of a minus f of a all over a minus a, but we saw that that's a problem, right? Because we would end up having 0 in the denominator and we can't divide by 0, so that doesn't work. So instead, when you use this idea of h getting smaller and smaller and getting closer and closer to 0, and what does that sound like? Oh yeah, it sounds like what we just spent a bunch of sections doing. That would be a limit. So here, to find the slope of the tangent line, we can really take the limit as h goes to 0 of the slope of the secant line from up above, right? Because as h gets closer and closer to 0, that slope of that secant line is going to become more and more the slope of the tangent line. And so what we're looking at then is f of a plus h minus f of a all over h. And that, y'all, that will be the equation or the formula for the slope of our tangent line. Pretty cool, huh? Yeah, I thought you would think that. Okay, so let's look at an example of this. So let's say we have this function f of x equals 4x minus 3x squared. And here they're asking us to find the slope of the tangent line. And after we find the slope of the tangent line, they'd also want us to find the equation of the tangent line. But let's start with just finding the slope of that tangent line. Okay, so we're going to use that formula that we have. So the limit as h approaches 0 of f of a plus h minus f of a all over h. And in this case, our value for a would be the value we're finding the slope of the tangent line at, so that'd be 2. So what we're really finding here is the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. And hopefully you notice at this point, there's not a whole lot we can do with that limit right now because we still have an h in the denominator. And so we can't like plug in h equals 0 because that'll cause us to divide by 0. And the numerator right now, all we really have is these representations of f of 2 plus h and f of 2, which are not going to be super helpful for us to work with. So what are we going to do? Well, up here, notice we have 2 inputs for a function f. So let's go ahead and input them into the function and see what happens. So we'll do f of 2 plus h, which give us 4 times 2 plus h minus 3 times 2 plus h squared. And for our purposes right now, I'll tell you that it will be helpful to simplify out that stuff on the right-hand side. And when you do that, make sure you're very careful about this 2 plus h squared. Don't just distribute the squared there. That will not get you the correct answer. You need to actually write out 2 plus h times 2 plus h. And if we do that, and skip some steps here, I believe what we get is negative 3h squared minus 8h minus 4. And then we can input 2. So we have 4 times 2 minus 3 times 2 squared, which is going to give us, I think, 8 minus 12, which is negative 4. Okay, so now we have those 2 values. So we go ahead and put them in the place of f of 2 plus h and f of 2 in our limit formula over there. So unfortunately I have to erase these for sake of space. Okay, so now I'm going to use this, make this up here. So our limit will now become this. We'll have the limit as h approaches 0 of, again, what f of 2 plus h is, which is negative 3h squared minus 8h minus 4. And then we're going to do minus. We need to be very careful here. F of 2 was negative 4, so we need to put that in parentheses. So it's minus negative 4 all over that h still. And you're thinking, Cody, this doesn't seem to be going anywhere. Oh, but I promise it will. Okay, so notice here in the, we'll do some simplifying. Notice we have the minus 4 here. We make a plus 4. And then up here we have a minus 4 and a plus 4, so those can cancel out. So now our limit becomes the limit as h approaches 0 of, we have the negative 3h squared minus 8h all over h. And this may be looking like, this still doesn't seem to work. But notice in the numerator up there, we have the negative 3h squared minus h. Those both have an h in common. So we can factor an h out there. And for the sake of space, I'm going to just rewrite this that way. So this will be h now times minus 3h minus 8, and we factor out the h. And notice now that h on the numerator can cancel out with the h in the denominator because it's now being multiplied by those things. And then we get the limit as h approaches 0 of negative 3h minus 8. And here, h is now in the domain of this function, or 0 is now in the domain of this function. So we can now plug in the 0 for h, and when we do that, y'all, looks like we get negative 8. And we have now found the slope of our tangent line. Okay, that noise is supposed to be the crowd going wild because I know you guys are all super amazed. Okay, pretty cool, right? We now have the slope of the tangent line. All right, so now that we have that, I'm going to go ahead and clear all this stuff out. And so we know the slope of the tangent line at x equals 2 is negative 8. Okay, so let's talk about the second part here. Now we need to find the equation of the tangent line now that we have the slope. So how do we find the equation of the tangent line? Well, how do we find the equation of a line? Well, we usually have to have a slope, which we have, and what else do we need? Oh, we need a point. Do we have a point? Well, we're working at the value x equals 2, which I think we did plug that into the formula, or into the function, right? And we did f of 2, which gave us negative 4. So it looks like now we have a point and we have a slope. So we should be able to find the equation of our tangent line. So recall that the general form for the equation of line, you can use this y equals mx plus b, or f of x equals mx plus b. We have the slope, which is negative 8, goes in for m. Then we also have a point, an x and y, so we can plug that information in. Okay, and then we can solve for the value of b here. So we'll have negative 4 equals negative 16 plus b. If we add 16 to both sides, I think we get b equals 12. So then our equation of our tangent line is negative 8x plus 12. Okay, and there we go. Pretty neat, right? Pretty cool stuff. Okay, and I just want to, before we move on, give ourselves a little visual of what we were just doing. So note, first of all, that the function f of x we're talking about here is a quadratic, right? We see that because it has the 2 here. We also know it's going to be a downward facing quadratic because of the negative 3 in front of the x squared. So the graph of this looks something like this. We were working at the point x equals 2, so right about here. And so what we found, again, is the equation and the slope of the tangent line at that point. So that would be this green line here. So it's a line that touches that graph at a single point and goes through where x equals 2. Okay? Cool. All right, let's look at another example. So here we have the function h of x, and actually, for clarity, I'm going to call this g of x, and you'll see why in a minute, equals root 3x. And they want us to find the slope of the tangent line now at the point x equals 1. So in this case, our value for a now is 1. And then we'll find the equation of the tangent line. So we can go ahead, set this up similar to the way we set up the last one. So we're going to do the limit as h approaches 0. We'll do g of a plus h. In this case, it'll be 1 plus h, and this is why I just chose to use g instead of h, is to not mess up our h's here. You're confused which h is which. Minus g of 1, and then we'll still have the h in the denominator. Okay. Now, in order to do this, just like on the last one, we need to find g of 1 plus h and g of 1. So we'll go ahead and plug those into our function. So we'll have g of 1 plus h equals the square root of 3 times 1 plus h. On the inside there, darn it. So, okay. On the inside there, we can distribute the 3. So we'll end up with root 3 plus 3h. We can also do g of 1, so we plug in 1 there, so we'll end up with root 3 times 1, which is just square root of 3. Okay? So now our limit becomes the limit as h approaches 0 of square root of 3 plus 3h minus square root of 3 all over h. Okay? And now we got to figure out how to take this limit. Now you may be looking at this saying, Cody, now the last one made a lot of sense because there was stuff we could simplify at this point. But here there are roots, and I don't know, can I cancel out the two threes under the different roots? And there's still that h down there in the denominator. Just don't know what to do. Well, don't worry, I'm here to help you with this. So first of all, the answer to one of your questions is no, we cannot cancel out these threes here. Even though they're both under roots, they're being subtracted, so we can't cancel them out. And yes, we still have that h in the denominator, so we can't take the limit quite yet. So what are we going to do instead? We have roots on the top that are causing some problems for us. What could we do? Oh yeah, we learned in our section on limits that one way to deal with this is to use the conjugate, right? So let's multiply this function by the conjugate of the top. So we'll multiply by 3 plus 3h, root 3 plus 3h plus root 3. Do the same thing on the bottom. So multiply root 3 plus 3h plus root 3. And we'll do some multiplying here now. And remember, on the top there, we have to FOIL this out. So do this times this, this times this, this times this, and this times this. So we'll start by doing square root of 3 plus 3h times square root of 3 plus 3h. That's going to give us just 3 plus 3h. So the limit as h goes to 0 of 3 plus 3h. Then we do root 3 plus 3h times positive root 3. But then we'll also do negative root 3 times root 3 plus 3h. Those will cancel out. And if we do negative root 3 times the positive root 3, that's just going to give us negative 3. And then in the denominator, we're going to just leave that as is. So we're not going to multiply that out. So do h times square root of 3 plus 3h plus root 3. And then hopefully see in the numerator now we have a positive 3 and a negative 3. Those can cancel out. So our limit here will become the limit as h approaches 0 of 3h all over h times square root of 3 plus 3h plus root 3. And notice now, even though that h on the top is with the 3, it's being multiplied. And the h in the denominator is also being multiplied by stuff. So we can actually cancel those out. And at this point, now we'd have 3 over square root of 3 plus 3h plus root 3. We can now input this value of 0 for h, because it's now in the domain of this function. So I have to erase some stuff over here to make room. Okay, so we're going to input 0 for h there. So what we'll have then will become 3 over square root of 3 plus 3 times 0 plus root 3, which is going to still give us a 3 on the top. If we think about it on the bottom here, this 3 times 0 becomes 0, so we'll have root 3 there plus root 3. You do root 3 plus root 3 gives you a 2 root 3, right? Okay, so it looks like our slope is 3 over 2 root 3. And let's rationalize this because we have a root 3 on the bottom. So if we do that, we'll have 3 over 2 root 3 to rationalize, very similar to what we're doing, multiplying by the conjugate. So multiply by root 3 on the top and on the bottom. If I do that, in the top, I'm going to have 3 root 3. In the denominator, the root 3 times the root 3 will become positive, or just 3 times 2 gives us 6. And then notice here we have 3 root 3 over 6. We can simplify the 3 and the root 6, so the 3 will cancel out. This will become a 2. And here we get our slope is root 3 over 2, which is kind of a neat number. Hopefully that looks very familiar to a lot of us from last quarter. So there's our slope, root 3 over 2. Okay. All right, so we have now that our slope of our tangent line is root 3 over 2. And now we can do the second part of this problem where we find the equation of the line, the tangent line. So we again need a point, which we can use our g of 1 equals root 3. So we'll set this up using the y equals mx plus b. And I know there's roots here that look a little scary, but we can handle this. So we'll plug in the information we have. We have a root 3 equals root 3 over 2 times 1 plus b will give us root 3 equals root 3 over 2 plus b. We can subtract root 3 from both sides, which if we do that, we'll have root 3 minus root 3 over 2, which we can make the root 3 a root 3 over 1, get a common denominator here, which would be 2. So if we do that, we'll end up with 2 root 3 over 2 minus root 3 over 2. So we have a common denominator. We can subtract the numerators. So 2 root 3 minus root 3 would just give us root 3 over 2 would be the value for b. Okay, so then it looks like our equation, our equation for our tangent line then will be y equals root 3 over 2x plus root 3 over 2. Okay, and there we go. We've done it. Found slopes of tangent lines and equations of tangent lines. Doesn't this just feel so wonderful? Aren't you guys just so proud of yourselves right now? You should be. Okay, so let's look at some of the theoreticals of this. So this first part up here is just summarizing what we had just found. So we can define the tangent line to f of x at a to be the line passing through the point a and f of a, and then having that slope that we've identified there. So our formula for the slope of our tangent line, the limit as h goes to 0 of f of a plus h minus f of a all over h. And we have some special vocabulary as well as some notation that goes along with this. So rather than saying the slope of the tangent line, we're actually moving forward going to refer to this as the derivative of the function. So by the derivative, we're referring to the slope of the tangent line. So we said the derivative of the function f of x at a, at the point a, denoted by, and we'll use this notation here, this f with that apostrophe. That means f prime is how we pronounce that. No, that doesn't mean it's a transformer, but we just say f prime there. So what we have now is that f prime of a is the same as that formula from up above. So the limit as h approaches 0 of f of a plus h minus f of a all over h. So that's our derivative there now. Okay? So relating that back to what we were just doing. So that first problem we did where we found the slope of the tangent line at x equals 2 for the function 4x minus 3x squared. So using that notation, we could write that f prime of 2 equals negative 8, since we found the slope of the tangent line at that point was negative 8. And another way to say this would be the derivative, or the value of the derivative at 2 is negative 8. Okay. Another example with this function here, and again, I'm going to call this g, not h. So we have that g prime of 1 equals root 3 over 2, because that was the slope of the tangent line, and or we could say the value of the derivative at x equals 1 is root 3 over 2. Got it? Cool. All right, one more thing. So let's suppose that we're given a graph, and we don't have the formula for the graph, or the function this time. And they want us to find the instantaneous rate of change at the value x equals 2. So here, at not that, at this value. Okay. Well, when we talk about instantaneous rate of change, what are they referring to? And I'll highlight even more that term, rate of change. What does that make us think of? Oh, right, the slope. They want us to estimate the slope at that point, which to estimate the slope, what could we use? Oh yeah, a tangent line, right? Now again, we don't have the formula of this graph, so we can't necessarily use that limit definition of the derivative we were just looking at, the limit definition of the slope of the tangent line. So what might we do instead? Well, let's just do our best guess here of what the tangent line might look like. So let's say maybe something like this, for example. Okay, that green line there looks like it might be a tangent line. And can we find the slope of that line? Well, hopefully you're saying the answer is yes, because remember, slope, not only is it that y2 minus y1 over x2 minus x1, but another way to think about it is rise over run. So what I could do is say identify this point here, identify another point on my tangent line, which looks like it goes through that point right there, about 322. And look at how much we rise to go from the first point to the second point. So it looks like we have to go from a value of 12 up to a value of 22. So we rose how much there? Looks like we rose 10. And then we run over to the right. Well, we go from 2 to 3, so it looks like we run 1. So our estimate for our slope, or our rate of change there, is 10. Okay. Whew. All right, we made it, y'all. That was really fun time. I'm glad you were here to join me for this. So that's all I have for now. Thanks for your attention.